Welcome back to the course Collaborative Robots Theory and Practice. So this week we'll be discussing on robot statics. So what is statics? Statics is a branch of mechanics that deals with the forces and torques acting on any physical system of a body that is in equilibrium with their environment, irrespective of the cause of these forces. So if you have, let's say you have a pulley which is shown here, so forces F, that is the pulling force, the tension force in the rope, and the force due to the gravity is keeping this pulley in equilibrium in its place. Let us say it is not accelerating. That means resultant of all these forces are 0 and the system is in equilibrium. So we won't bother where from these forces are arising. So that is what is statics is all about. So in case of robots, it becomes the link of the robot. So it may have a joint which is here, it has another joint which is here, and that further connects to various other serial chain system which is normally there in case of cobots. So most of the tasks that is performed by cobots are quasi-static in nature. You have already seen it. So as in case of assembling, surface finishing, collaborative manipulation, so all these cases, whole of the robot body almost remains not accelerating, right? So that means all the forces that comes on it actually making whole of the system in equilibrium. So statics becomes so significant in case of cobots. Okay. So in this module we'll have following lectures. So we'll first discuss on links and joint moments and forces. We'll extend it for recursive approach. Application of this is design of robot links and joints, controller design for precise manipulation, actuator selection and transmission design. As you can see, this is the robot serial chain. It may have a load which is coming over here from external side. It may have its own center of gravity, okay, which is actually pulling it down. Okay, so all the links may have its own weight, due to which there are many forces. There are independent isolated link may have forces coming because of the link prior to this and the link which is after this. So overall each of the link are in equilibrium, and we will study the effect of those forces on the link. Okay, so link and joint forces and moments will study. Okay. Controller design, you see in case of controller design, so whole of the control system which actually takes in the velocity inputs and the pose inputs, finally the robot moves. Okay, so you have to continuously apply certain forces, especially the gravity compensation forces, which is to be continuously applied. So overall this whole system, the control system design, will use the components of the forces which are derived due to the statics. Okay, derived due to the statics. And in case of actuator selection, these are the actuators. These actuators are selected based on the moments and the forces that are coming to the joints, which effectively is creating the torque at those axes. Okay. In case of transmission system, as I have already shown you earlier, if you remember, so in case of transmission system, this is a harmonic drive which I have shown. So transmission system becomes the part of the joint. So what is the torque which this can sustain? Okay, how much is the maximum torque these transmission system can sustain? There are belts, there are pulleys, there are gears. The forces that will arise due to the static forces, so that will be very helpful in selecting those gear, in designing those gears. Next lecture would be on gravity compensation. This becomes a major part of the control scheme when these forces, these gravity compensation torques that make actually the robot floating in the space, as if there is the robot is not acted upon due to the gravity. So if at all we make the robot gravity compensated, the controller becomes similar in all the direction. It is not in one direction you have gravity, so that makes controller very different, whereas if you compensate it, the controller becomes very much similar in all direction. Okay, so this is one of the major component, that is the static forces become one of the major components of any controller design. So we'll discuss on gravity compensation. Okay, designing algorithms for handling external forces and torques. So if at all robot is acted upon by any external force, how much should be the torque that is to be applied at the joint so as to take care of those external forces. So that we will study in this lecture. The third one would be on force and velocity ellipsoid and manipulability measure. Okay, so application is estimating the maximum velocity and the force a robot can generate in any configuration. Let us say the robot is in this configuration. What would be the force along different direction this robot can generate? Okay, so that is what we will be doing in this lecture. Okay, at the end, in the final lecture, I will use the theories which is covered in all these three, and I will try to create simulation model to demonstrate the theories which are covered in this lecture. Okay, so let us begin with the first lecture of the course, collaborative robot theory and practice. In this lecture, I will discussing on link forces and moments. So especially link of a serial chain robot, forces and moments. So this is a serial chain robot which finally terminates at one end and it is grouted to the ground. Algorithm for recursive computation of link forces and moments. Okay, so let us start with the link of a serial chain robot. Okay, so Mi is the mass of the link I. So this link has a mass of I. Fi minus 1 I, Ni minus 1 I are the forces and moments that are exerted on the link I by the link I minus 1 at OI. It is OI. These are the forces and moments. This is the forces and moment which is acting at this end of the link. Okay. Now Fi plus 1, Ni plus 1, these are the forces and moments exerted on the link I by the link I plus 1. So that link I plus 1 comes next to this link. Okay, so link I minus 1 will be the link which is before to this link. Okay, so this is OI plus 1 and I plus 1, Fi I plus 1 is basically the opposite of that. So if Fi plus 1 I is the force which is exerted by this link to the other one. Okay, so reverse is true with a negative sign at the same place. Okay, G is the acceleration due to gravity, as you all know. Di is the position of center of mass of the link, ith link Ci relative to the origin of the ith frame. So if this is the ith frame, so with respect to this di is the vector that connects OI to Ci. Okay, and that is a constant because once the link is manufactured, so that center of gravity is not going to change, that location is not going to change. Okay, Ri is the position of I plus 1th frame origin OI plus 1 relative to the center of mass of the link I. Okay, so this is Ri. So Ri I plus 1 is the components of this can be expressed as Rx, Ry and Rz transpose expressed in frame I plus 1. So this is the frame which is moving along with this link. So with respect to this Ri is not changing. Okay, so that is the permanent distances that we know, that is Rx, Ry and Rz, and that doesn't change with motion of this link because this frame is permanently attached to this link and it moves along with this link. Okay, Ai is the position of OI plus 1 with respect to OI. Again, this is equivalent to the link length vector. Okay, if you take magnitude of this, it is actually the link length, as you have seen in case of DS parameter also. So this again is a constant. So that is the distance between OI and OI plus 1. So it is the vector AI which is connecting the OI and OI plus 1. Okay. Again, QI is the rotation matrix that transforms the vector represented in the I plus 1th frame to the ith frame. Okay. So it is the link transformation matrix QI which can be extracted out of link transformation matrix AI minus 1. So it is the upper 3 cross 3 sub matrix of this is actually this. Let me just disappear for a moment so that you can see this. Yes. Okay. So now the force balance equation for this link would be, so the total forces which are coming from different directions on this link should sum up to 0 if I assume this link is not moving. So Fi minus 1I is the force that is acted on this link by a link which is prior to this, and there is a force which comes from the link which comes after this. So that is this one. Okay, and the force due to the gravity is MIG. So all these forces result to no motion. So ultimately the sum of these forces will become equal to 0. So this should form a closed vector triangle. So this is my force balance equation. Similarly, the moment balance equation taken about OI would be sum of all the moments should account to 0 again because it is not rotating as well, okay, in space. So Ni minus 1 I, that is this one, and Ni I plus 1 is this one, okay, with a negative sign, okay, and these are the raw moments which are coming on it, and then there are forces which are creating moment. So Fi I plus 1, so Fi I plus 1, so this is the force which is creating the moment because of this distance Ai, okay. So Ai cross Fi I plus 1. Similarly, Mg, gravitational force, would also create a moment. So Di cross Mig is the moment which is due to the gravity. So sum of all those should equal to 0, should be equal to 0. Okay. So now rearranging the equations that you have seen here 1 and 2, so it gives me this. Okay. So in terms of DH parameters, that is AI, that is the link length vector over here, AI vector, in the frame I is expressed as AI in I, because this is not going to change, this is a constant, because link length, when measured, different components of link length only varies with theta I, that is the joint angle. So AI in I is actually equal to AI cos theta I, AI sin theta I, and BI. BI is the offset, joint offset, as you know from the DH parameters. So this is my joint offset between OI and OI plus 1. So this is the distance travelled along z axis. Okay, if you take this, so this is your Di, earlier we called it Di, so this is Bi. Okay, so Bi is the offset and AI is the link length. Okay. Okay. So Di in ith frame should be equal to AI in ith frame minus Ri in ith frame. So all these should be equal to, say, AI directly comes from here. Ri now, Ri, if I want to express it in ith frame, it should be equal to Qi into Ri, Rx, Ry and Rz. Qi is the rotation matrix, okay, that is responsible to convert it to ith frame now. Okay, so let me just vanish, you can see it. So you see Ri in ith frame will be equal to Qi into Ri. Okay. So now coming to next. So the joint reaction moments and forces can be computed backward starting from the last link. From here you have to start when everything is more known. Okay, so you know the external forces which are coming on that. Okay, so everything is known for this. From there I would calculate for this one, I would calculate for this one and this one and this one, and finally till here. Okay, so the end effector moment n plus 1 n is the final link, that is the last link. So is equal to minus of n plus 1 and force Fn plus 1 n is equal to minus Fn n plus 1 are the known forces. Okay, so these are the known forces and moments. So whatever that comes on this is known. Okay, even if it is open to air, because of its maybe the end effector mass, some forces will come, so that is well known already. Okay, the reaction forces Fn minus 1 n and the moment n minus 1 n at the nth joint is calculated using equation 1 and 2. So you know, if you know the forces and moments over here, you can calculate over here using the equation 1 and 2 as I have shown earlier. Okay, so the process is iterated for links I varies from n minus 1, n minus 2, n minus 3 up till 1. So that way. So this was fully known. Using this you calculated this using equation 1 and 2, and then you moved backward iteratively and finally reached till here. Okay, the equations 1 and 2 of the ith link are first written in the I plus 1th frame, which is attached to it actually, that is not moving with respect to the link I. So they are converted to the frame I plus 1. Okay, once the reaction forces and moments are computed in I plus 1th frame, they are converted to ith frame using the rotation matrix Qi. This is the link transformation matrix, you can do that. And similarly for G, as G is specified in fixed frame, G is in fixed frame, so G has to be first converted to this frame. Okay, and then iteratively you can convert it back to this frame likewise. Okay, so you have to keep converting it. So first time you have to do conversion from this to this. Okay, that can be done using Qn, that is the last rotation matrix from here to here. If you know the forward kinematics transformation, so you have Q1, you have Q2, Q3, Q4 and Qn. The product of all those will give you Qn from O. Using that you can convert from here to here. Okay, so output of the end effector moment and forces that is specified in the fixed frame are also transformed into the end effector frame using this. So here is the rotation matrix Q extracted from the forward kinematics. So finally the outputs are all converted to the ground frame, that is the base frame, that is the robot fixed frame. Okay, using the rotation matrix Q that is extracted from the forward kinematics. So using that you can convert it. Okay, so now assuming negligible friction and other losses, the actuator torque and assuming the negligible friction and other losses, okay, the actuator torque for the revolute joint is this. So now that you know the moment at the joint, you project it along the axis of rotation and what you get is the torque at that axis. Okay, so torque that comes at that axis. So you just project it to that, you get the joint torque, and this is where it is used to select any axis joint actuator. Okay, for prismatic joint, the actuator force denoted by the same letter here, tau I would be the projection of force along the joint axis, and this will be helpful to select any prismatic actuator which you want to select. Okay, so where EI is the unit vector along the positive ith joint axis Zi. You know where from we can extract it? We can take it from homogeneous transformation matrix. Okay, so if this is N, this is O, this is A, so this is for the homogeneous transformation matrix up till the link I. For if it is for link I, the third column, first 3 rows will give you EI. Okay. So EI can be obtained using forward kinematic transformation matrix. Okay. So now you have extracted the joint torque and forces. You also know the boundary conditions for each of the link also. You know the forces and moments at both the ends of your link now. Okay, using that you can do FEM analysis and design your link also. Okay, so this is where statistics is very helpful in doing these tasks. Okay, so that's all for this lecture. In the next lecture, we will discuss on gravity compensation and resolving external forces and torques to joint forces and torques. So that's all. Thanks a lot.